Hello everybody, I hope you're well. Welcome to Chapter 4 in Unit 2. So before we left for March break, I asked you to spend some time in the weeks after March break, because recall we were told on the Thursday before March break that we wouldn't be back for a couple of weeks after March break, or perhaps longer. And as it is turning out, it is longer. I'm not sure when that's going to end, or if it will end, but that's a story for another discussion. So for today I want to start talking about Newton's laws of motion. Now what we studied in chapters 1, 2, and 3 were the motion itself. We studied how far an object moves, its delta d, its starting and final velocities, v1 and v2, its acceleration, and delta t, the time it takes for that motion to happen. So we talked a lot about the motion of the object. And in a lot of cases, we were using the 5 equations of motion, which were used to study accelerated motion for objects that have uniform acceleration. And remember I said that all 5 of those formulas only work if there is uniform acceleration. Uniform motion, which means constant acceleration. That constant acceleration could be zero acceleration, which is constant velocity, right? That's uniform acceleration. Or it can be uniform positive acceleration or uniform negative acceleration. Most things in the world don't have zero acceleration, right? There's a lot of motion. I mean, when we talk about motion, at the end of the day, if we're looking at objects that are accelerating, they accelerate for a reason. They accelerate because something is causing them to accelerate. We know that what is causing it to accelerate is a force. Something is pushing on the object, causing it to accelerate, or pulling on the object, causing it to accelerate. So this entire unit, chapters 4 and 5, are all about this concept of forces. So a force is something that pushes or pulls on any object. While you're sitting there on your chair, on your couch, on your floor, wherever you are right now, there is a force pulling on you, and that force we would know as gravity. Right? Gravity is pulling you down the whole time. We learned that when we're 2 years old, we first start walking. That's not the only force that's acting on you while you're sitting there. Right? While you're sitting there, whatever you are sitting on is also pushing you back. Right? Your body is not accelerating. Your body has constant velocity of zero. Right? Zero acceleration happening to your body right now because the forces that are acting on you are canceling each other out. They're both there, they're both real, but they will cancel each other out. Now, when we talk about forces, forces themselves are vector quantities. In other words, they will have a direction. The direction indicates which way, if there's only one force acting on an object, which way the object is going to accelerate. We know that if I hold an object straight out and I let it go, it will accelerate downward at a rate of 9.8 meters per second squared. The reason for that is because the direction of the force is towards the center of the planet. We know the magnitude of the force is causing it to accelerate at 9.8 meters per second squared, but we have not yet looked at how much force is being applied to that object. Do different objects have different amounts of force? So if one has a mass of 1 kilogram and one has a mass of 2 kilograms, do they experience the same amount of force? We do know that they will accelerate at the same rate of acceleration, but that does not necessarily mean that they will have the same force acting on them, even though they're both accelerating at the same rate. And maybe that's a bit of a clue for us as to where this is going to go. All right, so as we look at the fact that the forces are a push or a pull, and that the forces have direction, the forces therefore are going to impact on the motion of the object. Now, when we're looking at forces, the direction of the forces are going to be important because they will allow us to figure out which direction acceleration is going to happen. So for that object that we were just looking at a moment ago, it accelerates down because the forces are pulling it down. You are not going down right now while you're sitting there, because the force pulling you down is equal and opposite to the force pushing you up. And when I add those forces together, the negative force pulling you in the downward direction and the positive upward force being pushed on you by your chair, right, are going to cancel each other out. Now, in this course, we're going to talk about a number of different kinds of forces. In a lot of cases, if I have an object and I'm going to push that object, so let's say it's a shopping buggy, and I'm going to get behind the shopping cart, and I'm going to push that cart forward, right? That push on the cart is going to be an applied force, right? It's a force that's applied to the object. Typically, there's a number of things that can apply to a force to an object, but we're in a lot of cases, probably most cases, we're going to talk about a human applying a force or an animal applying a force. Could be a motor in a car applying a force. Could be a number of things that apply forces. We often will talk about gravity, because gravity is always there and it's something that's going to impact on all of our motion. In almost all cases, there is friction. Again, you know, when you rub your hands together, the friction will cause your hands to warm up, and this happens because the friction is the force of one hand pushing back on the other. And it's going to happen anytime we've got two objects sliding across each other, right? And we'll talk quite a bit about frictional forces as we work through this. Now, the normal force is the force that always pushes on an object away from the surface. So again, let's go back to you sitting on the couch right now, sitting on your bed right now, sitting on your chair right now. Gravity's pulling you down. The reason you're not going down is because your chair is pushing you away. The chair is pushing in a force which is perpendicular to the surface, right, 90 degrees to the chair itself. So if you're sitting on that chair, okay, here's a person, say you're standing on a chair, don't try this at home, right? The gravity is pulling down on the person, and the chair is pushing up on the person. So the person can stand there on the chair. Again, don't try this at home. Now, if there's a force of 100 newtons pulling you down, what I know is you're not going down and you're not going up, which means because there's 100 down, there must be 100 up. The chair is applying a force. Notice that you are perpendicular to the chair. You are 90 degrees to the chair, which is the direction of that normal force. So we have to consider that normal force whenever we're talking about an object in motion. Now, the other one that's often going to be used here is the force of tension. And tension is usually when we've got an object that's attached to a string or a cable or a rope or a pulley. And what's happening is I'm using that cable or string to pull the object. I'm not touching the object directly. I'm using the string as an intermediary between myself and the object that I'm pulling. Now, when I look at an object, such as the person standing on the chair there, I can see that if there's 100 newtons pulling down on the person and 100 newtons pushing up on the person, the 200s will cancel each other out, because I always, again, remember, have a sign convention, and for most things we use down as negative and up as positive. So that being the case, I've got 100 negatives and 100 positives, which will cancel each other out. And when I add them together, the sum or the net of the forces will be 0. Now, they're not always going to be 0, because not all objects have 0 acceleration. So what we have to do is we have to look at the forces as they are applied to each other in perpendicular planes. Forces that are up-down, forces that are forward-backwards, forwards that are left-right, right? Now, when I'm thinking about, again, think about pushing that cart across a grocery store. So here's the cart again, and here's the person pushing the cart, big cart. And as I'm pushing it across the floor at constant speed, 0 acceleration, right? The reason why there's 0 acceleration is because the forces being applied to that cart are, well, what would I expect? There's going to be a gravitational force that's pulling it down. there's going to be a normal force, which is pushing it up. There's going to be me applying a force in this direction, and then the object is going to be experiencing a force of friction, which is the reason why I have to keep pushing, and if I stop pushing the cart, it will stop rolling. It will grind to a stop. So what I'm looking at in this picture here is something called a free body diagram. A free body diagram should ultimately erase me from the picture and only leave in what are the forces that are applied to the object and what is their direction. So I can see here that there are 4 forces being applied to the cart. The acceleration, the applied force because of me, the frictional force working against me, the gravitational force pulling it down, the floor of the store pushing back up on the object. All right, so notice that my plane here, my forces are all working within a single plane, equal and opposite to each other, or within a single plane. I'm going to study the forces. So this force here, the frictional force here, and the applied force are working against each other, and they will ultimately, if the acceleration is 0 here, that means all of the forces are canceling themselves out. Right? I'm pushing, the friction's working against me. So just imagine yourself pushing a shopping cart down the virtual grocery store, which you're not allowed to go to right now. And as you're pushing your grocery cart at constant speed down the aisle, 4 forces are happening on that cart. Right? You, the friction in the wheels, the floor, and the gravity working on that cart. Gravity and the normal will cancel each other out, so it won't accelerate up or down. And the applied force and friction will cancel each other out. If I pushed that cart to the top of the stairs and then over the top of the stairs, the normal disappears because the floor disappears and the cart will go down because gravity is pulling it down. If the normal disappears, then I now allow the friction, the gravitational force, to pull the object in the down direction, and it will accelerate in the down direction. So in order to understand what's going on to all objects in the next month or so, say 3 weeks anyway, we're going to be drawing a lot of these free body diagrams. And what they do is they allow us to visualize the forces that are being applied to the object. I don't care what's causing the forces. All I care about is indicating what are the directions of the forces. 1, 2, 3, 4 forces in 4 directions, and what directions are the forces. So those arrows represent the forces. Right? The arrows are the vector quantities. And we've done this before, where arrows represent vectors. We did this when we were doing vector diagrams. A long arrow represents a big vector, a short arrow represents a small vector. Okay, I want to start here talking a little bit about Newton's first law of motion, which is the law of inertia. So when we talk about inertia, all objects have inertia, and the inertia present in an object is determined by largely its mass. So what inertia is it's a tendency of an object to resist a change in its state of motion. Whatever it's doing, it wants to keep doing that. Okay, think about your fridge sitting on the kitchen floor. It's not going to move on its own, right? In order to move it, you need a large amount of force to move it. Okay, think about a piece of toast that's sitting on the kitchen floor, right beside the fridge. It's pretty easy to move the piece of toast, right? It's not got a lot of inertia. Right? That fridge has a large amount of inertia. So inertia is proportional to an object's mass. Okay, let's think about 2 other situations. Think about a golf ball that's rolling down the hallway at school. Okay, so somebody uses a putter and putts the golf ball and it's rolling down the hallway at 1 meter per second. If you want to stop it, you could basically put your hand down on the floor in the hallway and stop it, no problem. It doesn't have a lot of inertia. Right? It doesn't have a great tendency to want to keep doing what it's already doing. Let's replace that golf ball with a bowling ball. If I roll that bowling ball down the hall and I want to stop it now, if I put my hand in front of the bowling ball, it might just roll right over top of my hand. right? It's got a lot of inertia. It's hard to stop it, right? So inertia talks about the tendency of an object to resist change in its motion, and largely the inertia is determined by the amount of matter that the object has. Okay, so an object that's at rest, heavier objects are harder to move, and for an object that's in motion, heavier objects are harder to slow down and stop. A bus has more inertia than a skateboard. Right? If you get run into by a skateboard that's rolling down a driveway and it runs into the back of your leg, right, not a problem. Right? If the rolling bus runs into your leg at the same speed, right, it's going to be a much bigger problem. The bus has more inertia. You're not going to stop it. It has a greater tendency to do, it wants to keep doing what it's doing, right? So you've got to work harder to change the motion of an object that has more mass. Okay, so the first law, basically, an object will maintain its state of motion unless it's acted upon by some external unbalanced force. Okay, unbalanced force means there's a greater force in one direction than in the opposite direction. Now, that's the first law. So we're talking about inertia. Inertia is the tendency of an object to maintain its state of motion. It says an object will maintain its state of motion unless something causes it to change its motion. Okay, so what are the implications of that law? Well, it says if there are no net forces acting on an object, if there is a net force, the object will change its velocity. It will accelerate. Remember, our definition of acceleration is delta v over delta t, a change in velocity over time. If the net forces are equal to zero, they are canceling themselves out, the object will maintain its velocity, whatever that velocity is. Think about the bowling ball rolling down the aisle. It rolls past Mr. Sinha's door going at 1 meter per second. It will go past Mr. Gupta's room at 1 meter per second. It will go past Miss Orban's room at 1 meter per second. All right? There are no unbalanced forces acting on the object. Right? It's a tiny amount of air resistance, but I'm going to pretend that it's negligible and it doesn't affect the speed of that ball. So what are the forces acting on that bowling ball? Gravity's pulling it down, the floor is pushing it up, and those two forces cancel each other out so the ball won't go up or down. But because there is no push on the ball in the forward or backwards direction, right, it will basically not have any net force. It will continue at its acceleration of zero. Now, if we think about a person, okay, I think I'm going to stop there for now. All right, so that's a lot for today. That's just looking at inertia. I want to come tomorrow I might come even tomorrow, Thursday, and look at Newton's second law, and then we will slowly start talking about Newton's second law. All right, so hopefully if you have any questions, please feel free to ask the questions. And some of you might have seen that I posted an answer to a homework question last night. If you go into the discussion forum, on the home page of our hub, you will find a question that was posed for one of the questions in the textbook, and I started to solve the question before I didn't have a calculator in the room that I was working in. I know I'm never without a calculator, but I'm a little out of practice here. So I will work on that question, but I will start into Newton's second law tomorrow.